Yesterday, we started section 4.1, but we did not get to finish them. Today, we are going to finish them, but we're going to have to keep going and not get to slow down much. But that's okay. Yesterday, I wanted to get a couple ideas across to you. Number one, I wanted to get across to you the idea that a radian, 1 radian, is a whole lot bigger than 1 degree. I wanted to get across to you the idea that 1 radian is a whole lot bigger than 1 degree. If I was to draw any random size, not that this is going to go up, that's okay. Any random size circle with the center-ish, with the radius-ish. With the center-ish, there we go, and a radius-ish. Approximately, like that. How much, remember, angle, standard position, starting right here, positive x-axis, moving counterclockwise or clockwise if I'm going positively? Counterclockwise, okay. How much would I rotate if I were to rotate 1 degree? About that much, right? Okay, 1 degree, think of a protractor, one little tick mark. Okay, 1 degree, there we go, there's 1 degree. That's an angle with a measure of 1 degree, right? So I'm going to go ahead and kind of approximate that. And that's actually probably a gross overestimation, but just so you can actually see it. Okay, that's 1 degree. How about 1 radian? Take 1 radius, right? Take 1, ooh, it's even bigger than my hand. Take 1 radius. Okay, take 1 radius. And what do I do with that 1 radius? I wrap it around. So approximately there. If I take 1 radius, if I make a measuring tape of 1 radius, if I go up here, and then if I wrap it around, 1 radius's length on the arc length would be 1 radian. Now, kiddos, can I use radians with nice whole numbers to get to perfect spots like 1/2 of the circle? I can get there, but am I going to get perfectly there? No. Because 1's going to be here, so this is 1 radian measure. So once again, what was 1 degree? Bitty little angle down there, right? That's 1 degree. What's 1 radian? Approximately 60 degrees, a little bit less. A little bit less than 60 degrees. But if I wanted to get over here, do you guys remember how many radians I would need? I would need to take this. 3 would only get me to about here. That would be about 3 radians. I need 3 point, no, I probably should have been a little bit lower, my approximation was a little bit off, but I need how many perfectly? 3.141592, I need pi radians. What did I say yesterday as an illustration to help us remember that pi, the angle 3.141596 radians is half a circle. How is that helping you remember that? Calzone. Gotta think of the half pizza.
Bam.
Okay? So 1 pi is 1 calzone. How many calzones in a whole circle? 2 pi. Got it. Right? So if I wanted you to get to something like 4/3 pi. 4/3 pi. How many slices do you have? Well, first of all, what have your calzones been cut into? Thirds, right? I'm going to use a different color marker because remember, these radians, they're not perfectly thirds or fourths or anything else. So I'm going to go ahead and cut this calzone into thirds. I'm going to cut this calzone into thirds. You can go ahead and erase, well, I'll leave the radian. So there are 6 slices total, right? 6 thirds. Oh, that makes sense. 6 thirds is 2 pi. Oh, 2 calzones. Got it. Okay. So if I were to say we have 4/3 pi, or 4 pi over 3, 4/3 pi, where are you at? 4/3 pi, you have these 3 slices and 1 more. Isn't this 4/3 pi?
Bam.
What if I was to give you a different angle? What if I was to give you 5 pi over 6? What have our calzones been cut into? 6ths, which means the thirds have been cut in half. Now I have 1, 2, 3, 4, 5, 6. But I have to do it down here. Okay. Do you remember what angle I told you? How many sixths do you have? 5 pi over 6, or 5/6 pi. So how many slices do you have? 5. So 1, 2, 3, 4, 5. you are 1/6 away from a whole calzone. What if it was 7 pi over 6? You have a whole calzone and another 6. What if you have 11 pi over 6? Oh, that's all 12, take away 1. And you can jump to places in the unit circle just by understanding fractions. What if I was to do one more, but I need another color marker and the red color? Here's what I need. Okay, so, what if I was to give you 7 pi over 4? What if my calzone's been cut into?
4 fourths.
Okay, now fourths.
So it's 1.
Wouldn't that be like a half cut into half? Right? So there's 2, and I can do the same thing over here. Okay, so I have 1, 2, 3, 4. Oh wait, that's happened down here too. How many fourths did I say?
7 fourths.
Okay, so I have 1, 2, 3, 4. 1, 2, 3. I have all 4 of those, and how many more fourths do I have? 7 over 4 or 7 over 4? I have 3 more. So I'm going to go 1, 2. Where am I?
Right there.
Some of you had a horrible time last year being able to figure out where these angles are in the unit circle when it's being given to you. It's just fractional pieces. So whenever they say 7 fourths, both calzones have been cut into fourths, go find me 7 of them. When it says 11 pi over 6, both calzones have been cut into 6, go find me 11 of them. If it's negative 2 pi over 3, you're not rotating counterclockwise, you're rotating clockwise. And negative 2 pi over 3, your calzones have been cut into thirds, and you're going how many of them? You're right here in the third quadrant. This is just to help you jump places in the unit circle, but we'll talk about a few other ways of jumping there today, because we're going to do some conversions, like how to get from radians to degrees. Some of you just like degrees so much better, you'd rather just take any radian given to you and just go to degrees and think that way. That's possible as well. But we have to talk about these, first of all, 3 different special types of angles: coterminal, complementary, and supplementary. Complementary, supplementary, you guys learned in geometry a long time ago. Coterminal, maybe not quite as fresh. Well, I guess geometry is not really fresh in your mind, but it was there once upon a time. Anyway, let's start with coterminal angles. Angles that share, oh sorry, did I ever finish my thought? 2 things I wanted you to understand yesterday. What is 1 radian? A whole lot more than 1 degree. 1 radius measured around arc length. But the second thing was, how do the unit circle angles work? Hopefully you understand how I was really trying to hit those 2 things yesterday. Today let's get some stuff done as far as getting some more terms down, getting some more examples done to help you get further in homework. Here we go, coterminal angles. Angles that share, co. Isn't co a prefix in English? It kind of means like with or together. Costco. That's not a prefix, but good idea. Prefix, like co-mingle, like co-habitate, like co-company. Company, no, that doesn't work. That's not a prefix either. What's another one? Co-worker. Co-terminal. There you go. So, what do they share? A terminal side. The co is just a prefix. They share a terminal. Co-co. That's just weird. Okay, so you're with the co? I don't get it. Anyway, so. Although shared is co that's always good. True friend is one that we share his people with. It's a little too sweet for me. Lucky Charms though. Ooh, yes. Or some granola with like some Rice Krispies or something. Pretty much good. Got some banana in there. Anyway, we're getting distracted. Measures that usually differ by, okay, we're actually going to figure out what this blank is. If I were to give you an angle, I'm going to give it to you in degrees first. Well, no, let's do radians first. We're trying to build that one. This looks like about a third of a calzone, right? Okay. Pi over 3. Let's also say, well, hold on, if pi is 180 and it's a third of 180, does anybody realize how that could be 60 degrees also? Okay, so a third of pi, a third of 180 is 60 degrees also. My question to you is, what's another way of getting there without going positive pi over 3 or without radians or without going 60 degrees? What's another way of ending at the same place with a different angle?
Negative.
Yeah, you could go negative. But guys, wouldn't you have to go negative everybody but pi over 3?
Yeah.
Everybody but 60 degrees? Now, you guys know 360 is a whole circle. So 360 take away 60, this would be negative 300. But can't you use our idea of radians? If it's all the all the thirds but one, well, you have 2/3, 6 pieces total. Take away 1, how many do we have? Cut the calzones into thirds. You have 1, 2, 3, 4, 5. You have all but 1. Because if you cut the top and bottom calzone into thirds, how many slices do you have? 6. You have all but 1. You have 5. 5 pi over 3. But it's negative because it's in the opposite direction. That's one way of getting there. Now, kiddos, how could we mathematically get from 60 to negative 300? What would we have to subtract from 60 to get? Yeah. So you can subtract 360. Does anybody know what we could subtract from 1 pi over 3 to get to negative 5 pi over 3? Negative 2 pi, or negative 6 pi over 3, which is the same thing. So, wait a minute, okay. What if we wanted to go positive, another angle? If we pass pi over 3, have you guys ever done that with those old alarm clocks where it's like you have to set the alarm for the next morning, but if you pass the minute, Yeah. Okay. So what if you pass the pi over 3 and we're turning positively? You can't backtrack.
You have to go all the way around.
Go all the way around. Wait, all the way around? Isn't that one full revolution?
Yes.
So what are you going to add to the pi over 3?
720.
It's a snail. Actually, there's a snazzy French word for a graph that looks like a snail called a limaçon. But we're going to talk about that another day.
Wait, that's cargo?
Not a dead snail.
Oh.
A live snail. Okay, way back. We have to add one full revolution. So in degrees, it's easy. It's 60 plus 360, right? What's 60 plus 360? 6 and 6 is 12.
420.
420 is one way of doing it. But what would it be in radians? What is a full revolution in radians? Or a full 2 calzones? 2 pi. So what's 2 pi plus pi over 3? Oh, that's hard. Wait, Chris, you said 2 pi in thirds. Same thing as what?
I don't know. I'm saying 6 pi over 3.
Yeah.
Oh.
He thought that it's 6 pi over 3 because he was thinking in thirds. Isn't 6 pi over 3, 3 and 3, 6?
Yep. Amen.
Yeah. So let's do 6 pi over 3 plus 1. 7 pi over 3. But either way, every time you have coterminal angles, angles ending at the same terminal, same ending side, they're always going to differ by a multiple of either 360 if you're in degrees or 2 pi if you're in radians. But maybe you think about the 2 pi as 6/3 or 8/4 or 12/6, just to help you out with the fractions. Or 4/2, I suppose. But the measures will always differ by a multiple of 360 or 2 pi, which brings us to basically a formula. Hey guys, what Greek letter? He's italicized. Imagine him straight up. What Greek letter? 5. Good.
Okay.
Alpha is this guy. He's like a little A.
Oh, I didn't know.
There's beta. And then there's, okay, we're stopped. So, this is 5. They just used another Greek letter because we already theoretically are going to use theta.
5?
5.
Oh.
Feed 5 to the fun. I smell the blood of the Englishman. Okay, so we can take an original theta and say a coterminal angle. A coterminal, this guy and that guy will be coterminal if one angle is the other plus 360n. The n just means multiples of 360, but I have to be careful because that n needs to only be negative and positive whole numbers. It can't be a fraction or else it's not going to be a whole 360 that I'm adding or subtracting. The negative is like subtracting, the positive is like adding. And there's a special name for all the negative and positive whole numbers. Aren't those just the integers, guys? If you want to be super snazzy, there is a symbol for integers just like there is for real numbers. It's a Z with a double line. If you want to be super snazzy.
Dang.
Real numbers, it's kind of like a paragraph sign. But integers, it's like a Z with a double line. But anyway, that's only if we're in degrees. I had to skip a line because what if we're in radians? It better differ by a multiple of 2 pi. Jacob.
What's the N for?
The n is just to say it could be theta plus 1 360. So we did 1 extra revolution, but it could be theta plus 2 360s, or 3 or 4 or 5. You could be twirling a lot of times and still ending on the same mark as long as you keep them full revolutions from theta. So the n just says multiples of 1 360, 2 360, 3 360s, 1 revolution, 2 revolution, 3 revolutions. Complementary versus supplementary. Back to geometry. Do you guys remember which one's which? Both of them are two angles that add up to be complementary. Which one?
90.
Good. Angles whose sum is, now, hold on, 90 degrees, or I'm trying to get you guys used to radians. What would it be in radians? 90 degrees, pi over 2. Good. Calzone cut in half, that's it. Or pi over 2. Now, real quick, there is a restriction to complementary. You've known since or learned since geometry. What kinds of angles do you need to be complementary? Acute angles. They have to be acute, meaning they both have to be less than 90 and add up to 90. Nothing like a negative, no, I should say nothing like an obtuse angle where you're subtracting another angle. It's not subtraction, it's adding two positive angles to be 90. I didn't know cute little angles. Okay, so. And there's the algebra. Yeah, I used to teach algebra. Coming back, supplementary. Supplementary. Same thing, angles. Don't have to be acute though. Don't have to be acute. But angles whose sum is, well, if it's not 90, what is it?
180.
And 180 is a half a circle or one calzone, so how many pi? 1.
1 pi.
Got it.
Ooh.
180 or pi. And I'm not going to say they have to be acute, but I am going to say they both have to be positive. And technically the first one had to be positive as well. I should have probably written that. The first one, just positive acute angles. The second one, just positive angles. They have to be adding to each other, not like subtracting, taking away. That won't work. So if I was to, on the following, give you, remember I'm trying to make you better at radians. If I was to give you something like, theta equals 3 pi over 4. Pause. Is that less than 1 calzone or more than? Less than is 3 over 4. So I'm only looking at the top half, right? I'm cutting that top half into how many pieces?
4.
And how many do I have? 3 of them. There's my angle. Question. What's the complement of 3 pi over 4?
1 pi over 4.
Complement adds up to be
90.
half. Is he acute?
No, he's obtuse.
So to get to 90, you'd have to subtract pi over 4, but is that legal?
No.
So there's no complement because he's too big. Anybody over 90 degrees, he's too big to have a complement. I can't add anything that's positive to him to get there.
They never find a girlfriend.
Oh.
No one knows.
Stop body shaming.
Coming back. What's his supplement?
Yeah.
What's his supplement?
Pi over 4.
Yeah, because you're just missing one piece, right?
Ah.
So all you're missing is 1/4. You have 3 to get to the entire pi. All you need is 1 more. So the supplement would be pi over 4. So guys, complements and supplements, it's what's missing. What's missing to get it to 90? Well, it already went past 90, so that didn't work. But what's missing to get it to be 180, or what's missing to get it to be pi? Well, I only need 1/4 more.
So then what if it's greater than 180?
Ah, no supplement either.
So he's never gonna have that.
Oh, trouble. So then, talking about both of them, it's only if it's less than whatever it's supposed to add up to, first of all, for it to be possible. And second of all, you're asking what's missing. Now guys, you could do math. For instance, you could have done what's pi over 2 for the complement minus 3 pi over 4. Now first of all, you would have had to get some common denominators, which is a little bit messy. But you would have had 2 pi over 4 minus 3 pi over 4. This one I'm trying to find the complement. I'm subtracting from pi over 2. I get a negative though, but am I allowed to have a negative? No. That's why I said, oh, no complement. But if I had done a little baby math problem with the supplement, pi minus 3 pi over 4. How many slices in a whole pie? How many fourths? 4 of them. What's left? So, for the supplement, I had it. For the complement, I didn't, it would have been a negative. Okay, so we talked about complements, talked about supplements, talked about coterminal angles. Let's talk about degrees. Oh dear, that's not good. Let's talk about degrees. Now, I basically already introduced this idea for you. Here's one whole radian, almost a third. Almost a third. It's a little off because a third of 3.1415926 is like a decimal. Almost a third. But 1 degree, well, it's 1/180th of a half. It's 1/360th of a whole. Like, how do you measure that? I don't know. Right? Measure of 1 degree. How do I define that to you? I don't know. I don't. Figure out how to split a circle into 360 equal slices and then take one. Well, that's kind of done. Now, it's helpful because your brains have been trained, so you know 90, 30, 45. Most of you can kind of just like picture the angles. But as far as mathematically describing what it is, well, I think it was something made up for an instrument to be pretty precise when doing like navigation. And that makes sense because they wanted tinier increments. And if you think of like cutting a radian into like really tiny increments, well, that's gross, it's decimals, and you're right. Radians would be awful for navigation. How do you get super precise with the radian? Well, I don't know. If you're thinking about this being the North Pole, the world's like a sphere, right? If you think about latitudes and longitudes, and if you think about the longitudes as being angles, I don't want to tell someone I'm in 1 radian. I want to tell someone I'm in like the 37th degree if I'm lost in the ocean somewhere. I need it to be precise. Now, I only did the longitudes and did the latitudes and whatnot, but you can think about with navigation, you need to be precise. Okay, they split a circle into 360, and even then, we're going to see at the end of the section, they took each degree and split that up also. Because if you take 1 degree, it's really tiny when the circle is really small. But what happens when the circle gets bigger with that degree? It slowly starts getting bigger and bigger and bigger, and if you make 1 degree, taking the entire circumference of the world and splitting that into 360, you can imagine 1 degree still takes up quite a lot of room. So they had to make a degree even smaller, but usually for our purposes, 1 degree is tiny, so radians are more helpful. Dimensional analysis though, how do you go back and forth? Ooh, we're building bridges. Yes, Mrs. Leon uses dimensional analysis. Maybe you don't remember the words, but she does. If I have 1 degree, and I want to go to radians, don't I need to get rid of the degree?
Yes.
So I need to build a bridge to get rid of what I don't want?
Yes, that's what she says.
So I need the degree on bottom, I need the radian on top, but in order to legally multiply by something, changing the form but not changing the value, I have to make sure it ultimately equals 1 in that they are equivalent. Like 1 foot, 12 inches. Same thing. It's going to change the form when you multiply. But at least it means the same thing. But guys, what is a radian that's equal to a degree? Or what is a degree that's equal to a radian?
360?
360 is 2 pi, or maybe easier.
Oh, 180.
180 is 1 pi.
I'm so smart.
That's it. That works. And then what's going to happen to my degrees when I multiply? Those units are going to cancel. And I'm going to end up with, well, if you want, we could actually make this 1 into like an x and say, I don't know what this is, but it's some number of degrees. So then when I multiply, I'm going to get, well, x times pi over 180, and I guess if you can reduce, reduce. Radians are not usually written as a unit. It's more of like a imaginary unit where it's not actually there. Kind of like if I say, go to the store, who am I talking to? Well, I guess in that moment, who knows, there are a lot of you, but I'm giving an understood you. If your mom looks at you and says, go to the store, hopefully you can drive or else you're walking. She's talking to you and you know that, right? Even though she didn't say you go to the store. Same thing here. If there's no degree mark and you know it's an angle, it has to be a radian. So, if you have something with degrees, you multiply, get rid of the degrees. Technically, a radian could be written by putting it in parentheses. It's an understood unit. Now, what if I am given a radian? First of all, if you're given a radian, sorry, that's a degree. I want it to be black. If you're given a radian, what's not going to be there? No degree mark. It's an understood unit. Radian's not going to be written. Not very often. So you're just given a number, you know it's an angle. Okay, to convert, I want to get a degree mark, which means the 180 has to go on top, but I have to make it equivalent, so what must go on bottom? Pi. I I could put radians if I really wanted to. And I could put radians, guys behind me. Can I spell radians? That was like an A in there somewhere. This one's not going to show radians, but it really means it. Pi's not going to write radians, but it really means it. In a way, we are canceling out the understood units. You just won't see it because it's not there to cancel out. You can always write it if you want. But when you solve, those radians are going to cancel out. And you're going to get x times 180 over pi. Now, kiddos, I suppose we could memorize the x times pi over 180 and the x times 180 over pi, but you know what I think is most useful? Understanding what to do. So instead of memorizing these ones as far as, hey, let's go ahead and get this whenever we need to convert, I don't want you to memorize them. Instead, I want you to memorize what to multiply by. But maybe it's something we can understand and we won't have to memorize. So that when we get to an example like this one. Oh, where's my example? Oh, he's missing. This is very sad. When we get to an example like, struggle. One of these days my smartboard and the projector will be friends. Okay. There we go. And I ask you to convert the following. And if I'm going to say convert, you should be able to look at it and know which way to convert. What if I was to say convert 50 degrees? It's not a nice unit circle one. 50 degrees. But then next I want you to convert 3. What would you do for the first one? What would you multiply? Because I have a degrees, so I need the 180 to go in the bottom, so that I get rid of what I don't want, right? So I would have 50 pi over 180, and then hopefully you guys would just naturally think of, oh, I should reduce that. That's going to be 5 pi over 18. The calzone was cut into 18ths, and you have 5 of them. They're in the first quadrant somewhere, not very high. Yeah.
Oh, I'm sorry, no,
okay.
I'm sorry.
So as long as you know what to multiply by, you should be able to finish. But what's going to be different down here?
It would be 180 degrees over pi.
There's no degree mark. It's an understood radian. Whether or not there's a pi, if there's a pi, we almost always think it's a radian. But whether or not there's a pi, if there's no degree mark, it's a radian. So I have to multiply by
180 over pi.
I need my radians in the bottom. I need the 180 up top. Think of it this way, I need the degree to stay. Now, what are you going to cancel out? Yeah, but they're not even there. So there's nothing to actually physically cancel out. It's more of just a, oh hey, I have a degree now, yay. And then I have 3 times 180, I think that's 540. If anyone wants to check me, over pi. You could do a decimal and figure out what that is. But long story short, the degrees are obvious to cancel out. The radians, you have to think about imaginary canceling. I don't know. But there you go. Okay. Finish off class today. We have some formulas to write because I said there were some applications. I'm going to go ahead and get, I think, all the formulas if I can find them. We already wrote down this one. No, we haven't written down that one. Let's see what we can do. All right, here's the first one. We've written down one formula so far this section. We wrote down actually theta, radians, is equal to arc length, S, over radius, R. We wrote down that one. All the formulas that we're about to write down, guys, are just applications or rearrangements of that formula. But what you need to know on every single one is that theta needs to be, for all of these applications, theta needs to be measured in radians. Degrees are great for navigation. Radians are important for any application as far as like physics. Talking about anything to do with actual arc length, distance around, we need radians. But you have to understand that because you're going to see a theta and say, plug in the degree, easy, like down here. The circle has a radius of 4 inches, r equals 4. Find the length of the arc. Find how far around the circle when I have a central angle of 240. What did they give me the angle in?
Degrees.
Degrees. So when I go to say, okay, find the length of the arc, well, the length of the arc we've already talked about is S. S equals R times theta. So I go to plug in, S equals 4 times, I can't plug in 240, I'm going to be way off. 240 has absolutely nothing to do with how long the circle is. It only has to do with 240 little tick marks of rotation.
Bless you.
So I have to take the 240 and do what? Convert to radians. So I need the degrees to cancel, right? So then who goes with the degrees? 180. What's equal to 180? Then my degrees will cancel. The zeros cancel, or reduce, I should say. 24 over 18, I think 6 goes into both, right? 4 pi over 3 times. That is the only theta that I can use. What you doing over there? Here we go. 4 pi over 3. S is equal to 16 pi over 3, which if we had a calculator, we would get that as a decimal, so we have some idea. 16 times 3-ish is 54-ish. No, 48-ish, sorry. Over 3 would be 16-ish, a little bit more. But long story short, guys, it's a word problem, so once we solve, make sure that you realize how long is the arc length. I need to put inches as my unit. It's not area, it's not volume, just inches, and we're good. That's one formula, that's one application, but remember, you need to put the angle in radians. But there are a couple more formulas that might show up. So let me go ahead and get you guys those formulas. Go ahead and get them down. We're not going to really get to practice them today, because there's one more thing I want to show you, and it's not going to be word problems. And now, guys, these word problems aren't like super big, complicated. You have to translate tons of stuff. It's more like look at the units and figure out if it matches the formula you need or not. But if you're able to get all of homework done up until the ones that talk about angular speed, linear speed, I'll be okay with that on Monday. I don't mind us going over a couple of word problems, but also there are good examples in the book how to use these formulas. But what I need you to know, every single formula with a theta needs the angle in radians, okay? And let me show you one more variation on this top one. Since S is equal to R theta, you might have to think about solving S over T by doing R theta over T. Otherwise, you're just getting them down so you'll have them in your notes. And the questions literally say, find the linear speed, find the angular speed, find the area of this portion of the circle. So there are examples in the book that go through how to use these formulas. But I'm letting you know now, it might be a little tricky, and that's okay. We'll go over the word problems on Monday. These formulas down. There's one more idea I want to show you, and it has to go back to what we were talking about how degrees, maybe not super helpful in physics when you're talking about circles that you guys deal with all the time and how small they are. 1 degree is very tiny. But with latitude and longitude and with navigation, 1 degree can actually cover a lot of area, so you might need to cut a degree up into smaller pieces. Those smaller pieces, cutting a degree up, is really hard for me to show you on a circle like this, because cutting that degree into 60 pieces, that degree was actually probably too big as it was. But there are times when the circle is big enough, like just think about our entire Earth, that degree needs to be cut up into something smaller, like maybe a minute. Now, a minute, I know it's a time measurement, but it's also a measurement of saying, hey, I'm cutting up 1 degree into 60 pieces. I'm sorry, not two apostrophes, just one is a unit for minutes. 1 minute is equal to 60 seconds. So not only are we going to split up a degree into 60 pieces. We're also going to take each of those pieces and cut them up into 60 pieces. We're talking about a huge circle that we really need to get really precise. We need an instrument that's able to measure, like in your guys' rulers, inches, they measure by like tenths. No, I think it's actually even 0.0. Is it fifths? Anyway. Our ruler is broken up into tiny measurements for us to approximate. Same thing here, 1 degree cut into 60 pieces, 1 minute cut into 60 pieces, which means, if you guys do some dimensional analysis, there are 3,600 60 times 60 seconds in a degree. And so if we're trying to convert, for instance, something like 3 degrees, 14 minutes, and 10 seconds, if that was given to us and we're trying to figure out what that would be as just a degree, what we could do is say, okay, if we were to take 14 minutes and say, well, that's 1/60th of a degree, and we could take 10 seconds and say that's 1/3600th of a degree, we could get it back into one number that shows us how many degrees that would be. Now, the sad thing is, this is way more precise than this, because this one will give us decimals and we'll have to round. Hence why minutes and seconds are really helpful. But we could go ahead and get a decimal approximation for the degrees by saying, basically, if you guys think about bridges, we would be multiplying by 1 degree over 60 minutes, and that's why it's 14 over 60, the minutes will cancel. Or multiplying by 1 degree over 36 seconds, and then the seconds cancel. It's a little bit harder, though, when you're given some sort of 14.35 degrees. It's a little harder when you go back the other direction. Because if you're going from degrees to minutes and seconds, here's the deal. We already know it's 14 degrees. We just need to figure out how many minutes and how many seconds. The 14 goes to the degrees. What's going to help me get to minutes and seconds? Just the fractional part. The whole number part, I can already make the degrees. I'm going to take the decimal part, the fractional part, and I'm going to do a little dimensional analysis with that and say, okay, I want to get to 60 minutes to get rid of that degree. Now I'm going to borrow Ryan's calculator really quickly. That's sad. I'm going to borrow Jordan's calculator really quickly. To do a quick multiplication, because I know some of you guys, if you don't have your calculators out, it takes you forever to get it going. So I have 0.35 times 60, and we get 21. The degrees cancel. Oh wait guys, do I even have any seconds? Do I even have any fractional minutes? Oh, okay, so then I just leave it, and I would just say 0 seconds. And that would be my answer, 14 degrees, 21 minutes, 0 seconds. But what if I was to give you another one, like, I don't know, 7.365 degrees? Question. Do I know anything off the bat? What can I fill in right away? 7. There's 7 whole degrees. What am I going to take down here to convert? What am I going to multiply by to get to the first one? 60 over 1. But when I multiply that, 0.365 times 60, I end up with, 21.9. Hold on. How many whole minutes do I have? 21. I'm going to take the 0.9, and what am I going to do to that? Go to seconds. So I continue the process. Now if I have 0.9 times 60, now I have 54. The minutes have canceled. Do you guys kind of see what I'm doing? I'm doing dimensional analysis, but not to everything. Because the whole 14 degrees, I wanted to keep degrees. The whole 7 degrees, I wanted to keep degrees. I only wanted to take the fractional or the decimal part and get rid of the degrees and try to get them into minutes. Because then the instrumentation that uses degrees, minutes, seconds can understand what's going on. For those of you guys that want to Google a little bit, the TI calculator does have degrees, minutes, seconds. You can try to figure out where it is. We'll reconvene on Monday and see if you guys were able to find where the calculator does it. But the one thing we were not able to do today, we were not able to do examples like linear speed, angular speed, area of a sector. You are plugging in, and if you do a theta, it needs to be a radian. If you get stuck on a word problem, look at the example. Good job, cool kids. Section 4.1, due on Monday. Pep rally schedule, I know it's weird. Our athletes have worked hard, they deserve it. Bye, guys. All of our athletes, all the different.
By the way, I got you back. And then
Have you even gone today with Allie now? No, it's not. I will never know.
You're lying.
I get to know these lying. I don't think we'll be done chapter 4 yet. Things are really good. Have fun on your cruise, bud. Is it a family thing?
yeah.
One day it's sunny, they get your contract.
Almost so nice.
Wait, it's warm in here today. But I know it's gonna happen. It's gonna get cold as soon as I put my jacket
Not
away.
picky, right?
I'm not gonna get chilled.
You don't do that.
I made that mistake yesterday.
Miss Black, do you know when the pep rally is?
Half of before.
Right before lunch, right after.
Wait, what's the pep rally for?
All the fall sports.
Yeah, I know. Like, I don't think.
Wait, why did you do
Send them into the
That
wild.
might be really choice. It's like crazy.
People care more about the
You
fall
want
sports
to
than
know when you want for winter.
Soccer.
Everyone cares about
Like, when's the last time you saw a pep rally for soccer?
Oh, was that the stupid alligator thing? Yeah, you went for basketball. They were like on the ground and they were like, that was hilarious. It was so boring. It was so funny. No one cared.
All you need is I had a room in here.
Oh, it's working here. The time I have two jobs. Oh, there you go. You were so ready. Alright, kiddos, it's open. Sorry, I had email stuff to deal with.